When people ask me why reality breaks at the smallest scale, I must first challenge the premise of the question itself. Reality does not break, not exactly. What breaks is our expectation that the rules governing the world we experience directly, the world of falling apples and orbiting planets and rolling billiard balls, should apply without modification to the realm of atoms and electrons and photons. What we discovered in the early 20th century, through a combination of experimental surprises and theoretical necessity, is that nature operates according to fundamentally different principles at the atomic scale. These principles are not broken or defective versions of classical physics. They are more fundamental, more general, and in a very real sense, more correct. Classical physics emerges as an approximation, a limiting case that works beautifully for large objects but fails completely when we venture into the quantum domain. Let me take you back to the beginning of my own journey into this strange territory. When I arrived in Cambridge in 1911 to work with J.J. Thomson, the discoverer of the electron, physics was in a state of crisis that most people did not yet fully appreciate. We had Ernest Rutherford's recent discovery that atoms consisted of a tiny, dense, positively charged nucleus surrounded by electrons. This nuclear model seemed inescapable given the results of his famous gold foil experiment, where alpha particles were occasionally scattered backwards as if they had collided with something incredibly small and massive. But there was a profound problem with this picture, one that any physicist trained in Maxwell's electromagnetism would immediately recognize. If electrons were orbiting the nucleus like planets around the Sun, they would be constantly accelerating as they change direction to maintain their circular or elliptical paths. And according to Maxwell's equations, any accelerating charged particle must radiate electromagnetic energy. This means the electrons should continuously lose energy, spiral inward, and crash into the nucleus in a tiny fraction of a second. Every atom in the universe should collapse almost instantaneously. But atoms are stable. The chair you sit on, the ink on a page, the cells in your body, all contain atoms that have existed for billions of years without collapsing. Something was deeply wrong, and classical physics had no answer. This was the puzzle I carried with me when I moved to Manchester to work with Rutherford in 1912. I was convinced that the nuclear model was correct, that the experimental evidence was too strong to doubt, but I was equally convinced that we would need to abandon or at least radically modify the laws of classical physics to make sense of it. The breakthrough came when I realized that we needed to import the quantum idea that Max Planck had introduced in 1900 for blackbody radiation and that Einstein had extended to light itself in 1905. Perhaps, I thought, the quantum was not just a trick for solving specific problems, but a fundamental feature of nature at the atomic level. My proposal was radical, even shocking to many of my colleagues. I suggested that electrons could not orbit at arbitrary distances from the nucleus but only in certain discrete, quantized orbits, which I called stationary states. In these special orbits, despite the fact that the electrons were accelerating, they would not radiate energy. This violated everything we knew from classical electromagnetism, but it solved the stability problem. An electron in the lowest allowed orbit, the ground state, would have nowhere lower to go and would therefore remain stable indefinitely. But how did electrons move from one orbit to another? I proposed that they made quantum jumps, discontinuous transitions where the electron disappeared from one orbit and appeared in another without passing through the space between them. When an electron jumped from a higher energy orbit to a lower one, it would emit a photon whose energy exactly equaled the energy difference between the two orbits. This explained the discrete spectral lines that elements emit when heated or excited electrically, a phenomenon that had been observed for decades but never understood. Each spectral line corresponded to a specific transition between allowed orbits. When I calculated the allowed energies for the hydrogen atom and predicted the wavelengths of its spectral lines, the agreement with experimental measurements was extraordinary. This was one of those rare moments in physics where a new theory makes precise quantitative predictions that match reality with stunning accuracy. It convinced many skeptics that I was on the right track, that the quantum was indeed fundamental to atomic structure. But even as I celebrated this success, I was deeply troubled by what I had done. I had essentially postulated that the laws of physics we knew, The laws that work so magnificently for everything from planetary motion to electromagnetic waves simply did not apply inside atoms. Electrons did not follow continuous trajectories. They did not radiate when accelerating in stationary states. They made instantaneous jumps between orbits. None of this made sense from a classical perspective. I had created a hybrid theory that used classical concepts like orbits but grafted on quantum rules that had no classical justification. It worked, but it was not satisfying intellectually. It was clear that we needed a deeper theory, one that was quantum from the ground up rather than a patchwork of classical and quantum ideas. That deeper theory emerged through the 1920s through the work of many brilliant physicists, particularly Werner Heisenberg, Erwin Schrödinger, Max Born, and Wolfgang Pauli. Heisenberg developed matrix mechanics, a formulation that dispensed with orbits entirely and dealt only with observable quantities like energy levels and transition probabilities. Schrödinger developed wave mechanics, treating electrons as waves described by a wave function that evolved according to a wave equation. These two approaches looked completely different but turned out to be mathematically equivalent, different languages for describing the same underlying reality. The new quantum mechanics was far more strange and radical than my original atomic model. In Schrödinger's formulation, the electron was not a particle following a definite path but a wave spread out through space. The wave function did not tell you where the electron was but gave you the probability of finding it at different locations if you measured its position. Before measurement, the electron did not have a definite position. It existed in a superposition of being at many places simultaneously. Only when you performed a measurement would the wave function collapse and the electron manifest at a specific location. This is where reality truly begins to break, or rather, where our classical notions of reality fail completely. In classical physics, objects have definite properties at all times, whether we observe them or not. A planet has a specific position and velocity at every moment, following a deterministic trajectory governed by Newton's laws. Even if we cannot measure these quantities with perfect precision, we assume they exist. But quantum mechanics tells us this assumption is wrong at the atomic scale. An electron does not have a definite position and momentum simultaneously. These properties do not exist in definite form until we measure them. The act of measurement does not merely reveal pre-existing properties but participates in bringing those properties into definite existence. Werner Heisenberg crystallized this insight in his uncertainty principle, which states that the product of the uncertainties in position and momentum must be greater than or equal to a certain minimum value determined by Planck's constant. This is not a statement about measurement limitations, as if our instruments are too crude to measure both quantities accurately. It is a fundamental limit imposed by nature itself. The more precisely you know an electron's position, the less precisely you can know its momentum, and vice versa. This is because position and momentum are complementary observables that cannot both have definite values at the same time. Let me give you an example that illustrates just how radical this is. Imagine you want to determine the position of an electron with great precision. To do this, you might shine light on it and observe the scattered light. But light carries momentum, and when a photon bounces off the electron, it transfers momentum to it in an unpredictable way. The shorter the wavelength of light you use, the more precisely you can locate the electron, but the more momentum is transferred, making the electron's momentum after the measurement more uncertain. Conversely, if you use long wavelength light to minimize the momentum disturbance, you sacrifice precision in determining position. You cannot win. Nature herself prevents you from knowing both properties precisely, not because of technical limitations but because both properties do not exist precisely at the same time. This uncertainty is not limited to position and momentum. It applies to any pair of complementary observables. Energy and time form another complementary pair. The more precisely an energy level is defined, the longer it must persist. Short-lived excited states have inherently uncertain energies. This is not measurement error. It is a fundamental feature of quantum states. But why does reality break in this way at small scales? Why does nature impose these strange quantum rules on atoms while allowing classical determinism for large objects? This question occupied me for many years, and I came to understand it through what I called the correspondence principle and later developed into the broader framework of complementarity. The correspondence principle states that quantum mechanics must reduce to classical physics in the appropriate limit. When quantum numbers become very large, when we are dealing with highly excited states or macroscopic objects with enormous numbers of particles, the predictions of quantum mechanics must approach those of classical physics. This is not an arbitrary requirement, but a necessity if quantum mechanics is to be correct, since we know classical physics works extraordinarily well for macroscopic objects. The reason reality appears classical at large scales has to do with a phenomenon we now call decoherence. Macroscopic objects are never truly isolated. They constantly interact with their environment through collisions with air molecules, absorption and emission of thermal radiation, and countless other processes. These interactions entangle the quantum state of the object with the quantum states of environmental particles in an incredibly complex way. The superpositions that would give rise to quantum interference effects get washed out, suppressed by this entanglement with the environment. What remains are classical probabilities rather than quantum amplitudes. The object effectively loses its quantum coherence and behaves classically. At the atomic scale, things are different. A single atom or electron can be much better isolated from its environment. It can maintain quantum coherence for significant periods, allowing superpositions and interference effects to persist. The quantum behavior is not hidden or averaged away. It is manifest and unavoidable. This is why reality breaks, or seems to break, at small scales. It is not that different rules suddenly take over. It is that quantum rules are always operating, but their distinctive effects only become apparent when systems are sufficiently isolated and involve small enough quantum numbers that the discrete nature of quantum states matters. Let me tell you about complementarity, because it is central to understanding why quantum reality seems so alien to our classical intuitions. I developed this concept through extensive discussions with colleagues, particularly Heisenberg, at my institute in Copenhagen. Complementarity is the idea that quantum objects have multiple aspects or properties that are all necessary for a complete description but that cannot be observed simultaneously. They are mutually exclusive yet complementary. The classic example is wave-particle duality. Light and matter exhibit both wave-like and particle-like properties, but never both in the same experimental arrangement. If you design an experiment to reveal wave properties, like interference in a double-slit setup, you cannot simultaneously observe which path individual particles take. If you modify the experiment to determine the particle path, the interference pattern disappears. Both descriptions are true and necessary, but they apply to different experimental contexts. The electron is neither purely a wave nor purely a particle but something more subtle that manifests different aspects depending on how you interrogate it. This complementarity extends beyond wave-particle duality. Position and momentum are complementary. Energy and time are complementary. Different spin components are complementary. In each case, you can design experiments to measure one quantity precisely or the other, but not both simultaneously. The quantum state contains information about both, encoded in the wave function, but this information cannot be extracted as simultaneous definite values. Why does nature operate this way? I confess I do not have a deeper explanation that would satisfy someone looking for a mechanism or cause in the classical sense. Quantum mechanics simply is the way nature works at the fundamental level. We can describe it mathematically with great precision. We can predict experimental outcomes with extraordinary accuracy. We can even understand how classical behavior emerges from quantum foundations through decoherence and the correspondence principle. But if you ask why nature chose these particular rules, why superposition and uncertainty and complementarity rather than classical definiteness and determinism, I can only say that this is what experiments tell us, what mathematical consistency requires, and what has proven to work without exception for nearly a century. Some physicists, most notably Albert Einstein, found this unsatisfying. Einstein believed that quantum mechanics, despite its enormous practical success, must be incomplete. He felt there should be a deeper theory with hidden variables that would restore determinism and give particles definite properties at all times, with quantum mechanics merely reflecting our ignorance of these hidden realities. He expressed this in his famous declaration that God does not play dice with the universe. I had many discussions with Einstein about these matters, some of them quite intense. I deeply respected his intuition and his philosophical commitments, but I could not agree with his conclusions. I argued that the demand for a classical-like reality underlying quantum mechanics was based on prejudices about what physics should be like, prejudices that needed to be abandoned in light of experimental evidence and mathematical consistency. Physics, I insisted, is not about describing some objective reality that exists independent of observation. It is about predicting what we will observe in precisely defined experimental situations. The question of whether particles have definite positions and momenta when we are not measuring them seemed to me to be a meaningless question, not because we lack knowledge but because the question presupposes concepts that do not apply at the quantum level. It is like asking what color a musical note is. The question itself is confused because it tries to apply a category from one domain to an object in another domain where that category does not apply. Many years after these debates, physicists developed experimental tests that could distinguish between quantum mechanics and any theory based on local hidden variables, the kind of deeper deterministic theory Einstein hoped for. These are tests of what we call Bell's inequalities, mathematical constraints that any local hidden variable theory must satisfy but that quantum mechanics violates. The experiments, performed with increasing sophistication from the 1970s onward, have consistently confirmed the predictions of quantum mechanics and ruled out local hidden variables. These results mean that if you want to restore some kind of objective reality underlying quantum mechanics, you must give up locality, the idea that influences cannot travel faster than light. You must accept what Einstein called spooky action at a distance, the instantaneous correlation between distant parts of an entangled system. Or you must give up realism, the idea that objects have definite properties independent of measurement. Most physicists, myself included, prefer to give up classical realism rather than locality, accepting that quantum mechanics is telling us something profound about the nature of reality itself. So why does reality break at the smallest scale? It breaks because the classical picture of reality, with objects having definite properties following deterministic trajectories in space and time, is an emergent approximation that works for large, complex, environmentally coupled systems but fails for small, isolated quantum systems. The quantum world is the fundamental reality. It is characterized by superposition, uncertainty, complementarity, and the crucial role of measurement in bringing definite classical properties into existence. The classical world we experience is built on this quantum foundation, emerging when quantum systems become sufficiently large and entangled with their environments that quantum coherence is lost and classical behavior appears. But I want to emphasize that this is not a breakdown or failure of nature. It is not as if nature tried to be classical but could not quite manage it at small scales. Rather, nature is fundamentally quantum, and classical physics is the approximation, the special case. What seems like a breakdown is actually our cognitive limitation, our difficulty in visualizing and intuiting quantum behavior because our brains evolved to deal with macroscopic objects where quantum effects are negligible. The mathematics of quantum mechanics is perfectly consistent and unambiguous. The Schrödinger equation tells us exactly how wave functions evolve. The Born rule tells us exactly how to calculate probabilities from wave functions. The uncertainty relations tell us exactly what combinations of properties can be measured simultaneously. There is no breakdown in the mathematics. The breakdown is in our ability to translate this mathematics into simple visualizable pictures that satisfy our classical intuitions. I have spent much of my life trying to help people understand this, trying to articulate what quantum mechanics is really telling us, trying to develop the philosophical framework of complementarity that makes sense of the apparent paradoxes. It has not been easy, because the temptation to think classically is so strong. We want particles to be little balls with definite positions. We want them to follow definite trajectories. We want measurement to merely reveal pre-existing properties rather than participating in creating them. But nature does not accommodate these desires. When I look back on the journey from my initial atomic model in 1913 to the full quantum mechanics of the late 1920s and beyond, I am struck by how much we learned and how much our understanding of reality had to change. We learned that electrons do not orbit nuclei in the classical sense. We learned that atoms exist in discrete energy states separated by quantum jumps. We learned that particles have wave properties and exist in superpositions. We learned that measurement plays an irreducible role in quantum mechanics. We learned that complementary properties cannot be measured simultaneously. We learned that nature is fundamentally probabilistic at the quantum level, with determinism emerging only in the classical limit. Each of these lessons required us to abandon some cherished classical notion about how reality works. Each caused confusion and debate. Each seemed paradoxical or impossible until we learned to think quantum rather than classical. And each has been confirmed by countless experiments, not just confirming the broad outline but verifying the precise quantitative predictions of quantum mechanics to extraordinary accuracy. The reality of the quantum world is not broken. It is strange, counterintuitive, and profoundly different from our everyday experience, but it is not broken. It is simply quantum. And learning to accept and understand this quantum reality, learning to work with its mathematics even when we cannot fully visualize its mechanisms, learning to appreciate its subtle beauty and its deep implications for the nature of existence, this is one of the great intellectual adventures of human history. Why does reality break at the smallest scale? It does not break. It reveals itself in its most fundamental form, a form that transcends our classical intuitions and demands that we think in new ways. The quantum world is not a defective classical world. It is the real world, the foundation on which everything else is built. And recognizing this, accepting the strangeness and working through the conceptual challenges, is what it means to truly understand modern physics. I have watched quantum mechanics grow from a few puzzling observations and bold postulates to a complete, mature theory that undergirds all of chemistry, most of physics, and increasingly our technology. Quantum mechanics has been tested more thoroughly than any other theory in the history of science, and it has never failed. Every prediction it makes, no matter how strange, has been confirmed when the appropriate experiment is performed. This is not the mark of a broken theory or a reality that fails at small scales. This is the mark of truth, of having discovered something genuine and deep about the way nature actually works. The reality of the quantum world is that it is probabilistic, complementary, non-local in certain respects, and fundamentally intertwined with the act of measurement. These are not defects or approximations. They are features of the quantum reality that underlies all physical phenomena. Classical physics, with its determinism and definite properties and separability of observer and observed, is the approximation, the limiting case that emerges when quantum effects average out for large systems. So when you ask why reality breaks at the smallest scale, I invite you to reframe the question. Reality does not break. Our classical picture breaks, revealing the quantum truth that was always there, operating at all scales but manifesting most clearly at the atomic and subatomic level where quantum discreteness and coherence cannot be ignored. This is not a breakdown. It is a revelation, perhaps the most important discovery in the history of physics, and it has transformed our understanding of nature at the most fundamental level.